Move on, Mike.
All right. So we're videoing, so I have to. So good evening, everybody, and welcome to I don't know if this is our third or fourth idea talk of the spring 2018 term. Thank you to Alex New, math PhD student, for this talk. It's work that's related to our the project that we have going on, the HEALS project, which is our big multi-year health research project with IBM, which is getting increasing amounts of attention. We're very excited. There's HEALS actually has two different projects. One is more related to a sort of a personal health assistant, and the other is more of a clinical setting, like a physician assistant based. Both are based roughly on machine learning and those sorts of things. And Alex is going to dive into this with one of the projects related to that second work. So just a couple of things. This is being streamed and recorded live, so you're welcome to ask questions. These talks are meant to be interactive, so please ask lots of tough questions of Alex. He can handle it. And I think that's about it. All right. Take it away, Alex.
Oh yeah, hi everyone, thanks for coming. So today I'm going to be talking about using semantics and analytics for dynamic precision health risk analyses. That's a lot of buzzwords, I admit, so we're going to try to unpack what this means and get a better feel. So our motivation is that we have some sort of researcher who's interested in harmful conditions such as breast cancer or heart disease or that sort of thing, and they have some possible set of risk factors. And like these risk factors could be your urinary exposures to certain heavy metals, or how much TV you watch, or whatever. And you want to know, like, are these risk factors associated with the condition? And there's a couple of ways you could ask this question. You could say, on the level of an entire population, is there an association? Or you could scale down and say, for some specific subpopulation, is there a vulnerability? So are people of a certain ethnicity or people from a certain region in the country, do they have some notable susceptibility or resistance to these risk factors? And so then you can break that down into two cases. So either you know what these subpopulations are ahead of time through some sort of domain knowledge, or you want to use the data to discover them. So this is a pretty broad set of questions, and it's has a decent number of applications, and it's useful. And so then what we also want to know is, can we use semantics to enable understandable and scientifically rigorous risk analyses? So what we mean by semantics here is some sort of formal vocabulary that computers can interact with in a very broad sense. And we're talking about having some sort of heterogeneous data. So like in sort of standard data analysis, you have a vector of numbers, and each of these numbers has some possible association with targets. And so here we're looking at cases where instead of having a vector of numbers, you have a more complicated relationship. So some quantities you associate with observations have utility purposes. Others might not be directly used for prediction, but can still be used for other things, that sort of thing. So you're working with like sort of complex data sets. And so the term that we've coined, I think, is this semantalytics. So some sort of integration of semantics and analytics for interesting purposes. And then what I'm going to be focusing on today is this risk browser. So the risk browser is a way to do dynamic risk analysis that's like sort of semantically enabled. And so we've developed this risk browser in R-Shiny, which is a package for the R language. So I'll try to demo it later in the talk once we try to give an overview of why it's a useful concept. So what have we done so far? We have an ontology for study design. And so if you don't know what an ontology is, you can think of it as, again, some sort of formal vocabulary that's useful for some domain or some subject. And if you have this vocabulary, you can make deductions about entities in it. you can make inferences, and so you can sort of expand your overall knowledge. And so using this ontology, we can represent the different variables in our analysis, and so like what they do, how they are. We can develop graphs, so the computer science graph, not like a visualization for semantic integration. And however, so we're using graphs for metadata specifically. So the analytic techniques we have at our hands right now are mostly oriented around that tabular format for data, where you have just essentially a CSV of observations and features. And so if you extend that into a graph format, you get a bit more expressive power, but the computational time and general difficulties of analysis get more important. So we're going to make our problem simpler by basically relying on metadata for the graph parts. So metadata are things like what purpose a variable has. Is it a continuous variable? Is it a discrete variable? Who measured it? Where did it come from? That sort of thing. And so the advantage of having an analysis ontology is that you can store expert opinions. So you can look at domain literature for specific problems, and then like learn interesting things from that literature and store it in the ontology to make better overall analyses. So if some domain experts think that if you're looking at diabetes, it's really, really, really important to adjust for age, then you can store that in your ontology and have that there for future analyses. And then we can also extend this to new types of problems. So the ontology we have so far is a limited set of target conditions, but you can add as many new target conditions as you want just by adding them into the ontology, and then everything scales with that. So you have some scalability. And so the class of analysis we're doing is this environment-wide association study, or EWAS. And so what the EWAS is so like I said, you have some list of possible risk factors, and then maybe a set of controlling factors. And so you look at the risk factors one by one and look for their association with the target condition while controlling for the control factors. And then you aggregate your results in some sort of visual manner and also numeric manner. So I have a reference to the original paper, I think, for the EWAS, but it's very commonly used. We've noticed, I think, about 500 papers on PubMed that do this general sort of thing. So if you can represent this with an analysis ontology, then you get a lot of ability for paper replication. And so, like I said, we're looking at 3 levels of analysis. So either in a population, on a predefined study cohort, or on some sort of data-determined cohort, which we call cadre analysis.
I have a quick question.
Yeah.
So you said you mentioned about adjusting for age in the ontology.
Mm-hmm.
Can you elaborate it?
Yeah. So when you store a condition in your ontology, so when you store the things related to like diabetes 2, then you can have attachments to the node for diabetes 2 that say good control variables are age, good control variables are gender, or something like that. So you can by looking for a specific condition in your analysis ontology, you can learn about what things you should try to control for.
Okay.
Does that make sense?
You basically select data based on the control variables you define in some ontology. Is that?
Yeah. Any other questions, anything like that? So this is just a basic overview now that we've done some initial stuff. So an interesting paper that's from a couple of years ago that's doing something similar is this paper by Neural et al. And so what they have is an analytics ontology for model selection specifically. So in analysis problems, you will sometimes have to deal with model selection. So you have an analysis question. I want to find the relationship between y and x. And so then you say, what sort of model should I use? Should I use ordinary linear regression? Should I use a support vector machine? Should I use a convolutional neural network? And someone who's trained in data analytics can answer these questions for you. But if you're not really a data analysis person and you're more of a domain expert, then it can be hard to answer those questions. And so having an analytics ontology does that decision process for you. And so there are three major components to their analytics ontology. You have background knowledge, which is the analytics ontology axioms. So you say, this is basically just characteristics of models and what conditions they're appropriate. So you say softmax regression is a generalized linear model that models noise with a multinomial distribution. Then you have your observations, which is the characteristics of whatever data set you're working with. So the Fisher-Iris data set, which is a pretty common data set used in just toy analysis, has a discrete response variable with 3 values and then 4 non-negative continuous predictor variables. So you have, they have like a scheme that will look at a data set and extract this information. And then you combine your background knowledge and your observations into an explanation. So what models are preferred for this analysis question? So an example conclusion could be softmax regression could be used for the Fisher-Iris data set because the response is discrete, but not binary. And so, it can like plug in different data sets and different models to get these justifications for what you should do. And like I said, it's more accessible to someone who's not really a specialist in machine learning. But the issues with this paper are that they're limited to a very specific study design. So they cannot handle our environmental wide association study. They really only look at one specific response, and they are a fixed set of predictor variables. So it's not the most generalizable analytics ontology, and there's room for improvement. And their model selection decisions are also pretty basic. So if you're like talking about a more complicated model selection process, that would be like, how do you choose the architecture of a neural network? And that's very difficult compared to, should I use ordinary linear regression or should I use logistic regression? And so they don't really handle these harder problems. But what they do have is this framework called scalation, which is based on the Scala language. And so you can see right here, mouse over it. So this is an example of a model justification. So you have your data set, which is MPG, cylinders, displacement, horsepower, weight, acceleration, model year, and origin. So these are all your variables. The ontology has extracted their characteristics, and then it's come up with justifications for what sort of models you could use. So they're saying, in this case, you could either use multiple linear regression, or you could use ANCOVA. And then if you read this, it says why you would want to use these models. So you have these semantics-driven explanations for what models are preferable, which is pretty nice. And then on the right, we have just a graphical representation of a data set. So the same information you get here, basically. So all the different variables, these are your predictor variables. The MPG is the target, and then what characteristics they have. So this is a pretty interesting work, and it's what we're looking at this sort of thing for our own work because it does some nice things with both semantics and analytics. So to go into a little bit more detail about the environmental wide association study workflow, we have this nice diagram right here. So how this workflow works is you say, okay, what sort of people am I interested in? Do I want people who were studied in a certain year, who have a certain range of BMI or a certain age range, that sort of thing? Do I want to look for associations with diabetes 2 or coronary heart disease? Then once you've done that, you say, okay, what do I want to control for? And then the model ontology has recommendations for what you want to control for, but you might want to go against those recommendations. We might want to try something new. And then your study variables, which is the risk factors you're actually looking for associations with. And then once you've made these selections, the model does pre-processing. So if you have variables that are very right skewed, then it's used to log transform them, so it does that. If you want to compare variables that are on different scales, you might want to standardize them, so it does that. Then for our specific problem, you're dealing with a complex survey design, and so you need some kind of interesting stuff with survey weights. So you do that, and then you also have to handle any missingness in the data. And then finally, the model type depends on whether your target variable is continuous or discrete. So if it's continuous, then you can use linear regression, and if it's discrete and binary, then you can use logistic regression. then this is just an overview, a little bit more of an overview of what we mean by risk. So you're finding risk factors with respect to control variables and study variables. The big things are these bullet points right here. So what we care about in the end are having some sort of p-value, so which is how the probability that we've observed a connection between the study variables and the target by chance, then a regression coefficient, which measures how strong the relationship is between your target and your study variable, and then a standard error, so how precise your measurement of the regression coefficient is. These are all pretty standard things in statistics, so most of you probably know about them. But when you're doing this sort of large-scale modeling, you want to have this sort of basic information. And then finally, when you're doing an EWAS, you generally have a lot of comparisons you're doing, so you're generating a very large number of p-values. And so it's common to do some sort of procedure for false discovery rate correction. And the one that we've done is Benjamini-Hochberg, which is pretty standard. So the data set we're working with for the risk browser is NHANES, which is the Continuous National Health and Nutrition Examination Survey. So every 2 years or so, it surveys about 10,000 people in the US. And there's a lot of complexities in how exactly that's done. So not every variable is measured in every person. Not every variable is measured in every year. And then the data are de-identified, so you can't really use the NHANES survey to look up any specific people. In addition, it's a cross-sectional survey, so there's really no ability to track people as they change over time. You just got a random slice every 2 years. And so then there's different components of the study, so demographic information, which is often useful for controlling. Then what we really care about here is the laboratory stuff, because that's where you get things like environmental exposures and that sort of thing. And so the other two things about NHANES are you have a very complicated missingness structure, and then you have that survey design. So this is a visualization of the missingness in NHANES. So the way you read this plot is every row corresponds to a single person's measurements. And then every column is a different environmental exposure variable. And so then a cell is blue if there's a measurement for that person, and it's red if there's no measurement. So as you can see, no person has a measurement of every variable. Many variables don't occur in many years. So you have to do a lot of data cleaning by hand or data preparation by hand when you're working with NHANES. And so the advantage of the risk browser is that it does most of this preparation by hand not by hand, but just for you. And so there's less chance for you to make a mistake in your preparation or that sort of thing.
This for in all the years that was ever measured?
This is 1999 through 2014. But it's only about 180 exposure variables. I think there's closer to like 10,000 variables total, but many of those are not particularly interesting or useful.
This includes redundant variables, right? So,
oh, sorry, what?
The 180 exposure variables, that includes redundant variables that were named different dynamically.
I don't think so. I think that so another complexity is not every variable has the same name in every year, but this, I think, takes care of that for the most part.
Okay.
Yeah, but I'm not totally positive.
This was generated from the NHANES, a data that was pre-processed already to remove those redundancies, is what you're saying?
Yeah, so there's a package called NHANES that is pretty good at extracting most of the NHANES data directly into an R format instead of working from like a SAS format or something like that.
So that sequence number throughout the years, is it the same for the same patient?
So you really don't get the same person in 2 different years. Since it's cross-sectional, if you're sampled 1 year, the chances of being sampled another year are vanishingly small. So there's no ability to track people. So every survey year gets a different set of 10,000 possible ID numbers, basically. So now just some more ideas as to like why survey analysis in particular is challenging. So in most machine learning and data analysis methods, you make some sort of IID assumption. So you say the data you're working with all came from the same distribution and they're independent of each other. And this works well for modeling when additional observations are fairly easy to acquire, and we don't plan to examine very small subpopulations individually. So this works pretty well in like image data, for example, because you can always pull more images off of the internet. But when you have a single person who's like going around and taking measurements of people, it's more difficult and expensive to get very large data sets. So what statisticians have come up with is this complex survey design. And what this lets you do is you oversample certain subpopulations relative to their place in the data, overall data set. So if there's a certain subpopulation that you really care about, which is maybe like elderly Hispanic women, because there's research out there that says that elderly Hispanic women are extremely at risk to some factors. You know people are going to want to use NHANES to look at elderly Hispanic women. Then you can oversample elderly Hispanic women relative to their size in the population, and that gives you a greater statistical power. And so that's useful, but the bad thing about survey analysis is that you've violated IID, and so you can't use standard methods. So you have to use this idea called pseudo likelihood estimation, which is kind of complicated. Luckily for the risk browser, there's a package in R that does most of this for you. And so what we really have to worry about is just constructing the right survey weights. And so a survey weight is a number assigned to every person that roughly says how important they are relative to just like a random draw. So that's survey analysis. And just as a quick aside, what you want to note is that using these survey weights is very important if you want to get good results. So what we have here is we're seeing how associated gender and ethnicity are with BMI from some slice of NHANES. And we're using 3 different models. So an unweighted linear regression, so a model that doesn't use any of the weights. A weighted linear regression, so it uses the weights, but not all of the complex survey design. And then the full survey weighted linear regression. And so that's the survey weighted, unweighted, and weighted. And then so each of these triples of numbers is the set of regression coefficients for that model. And then the bars are 95% confidence intervals. So what we see here is that some of the time using the weights doesn't really change your conclusions. But so for finding the relationship between gender and BMI, the unweighted model has a very different regression coefficient than the other 2 models do. But what we can also see here is that even if you don't use the complex survey design and you only use the weights, then you still do pretty well. So the blue error bars track pretty closely with the red one for the most part, which is useful when you can't work with all of the survey data because of modeling limitations.
So you're not learning the weights in the regression, you're using the weights for the weighted, for GLM WTD, you're using the weights from NHANES, but just not the survey package in R?
Oh, yes.
Okay.
Yeah, so you're just supplying the weights argument, basically. Okay, so now the precision part of my title, what does that mean? So we have 3 levels of modeling. Like I said, we can fit a model to an entire population. We can choose a specific study cohort, or we can try to learn an informative subpopulation. And what the ideal case is that you already know what your subpopulations are. And in those cases, you can just use them and you don't need to learn them. But when you can't learn them, which is some of the time, then it's important to have some sort of model that can discover them. And so we have that. It's called the idea of cadre modeling. So the idea talk I did last semester talks about it. And then we have a paper in the archive that lays out the gory details. So I don't really want to focus on those details here. But what you want to know about cadres is that they're subpopulations that are chosen for a specific supervised learning problem. So it's not clustering. You're choosing the definition of your subpopulations with respect to some specific metric instead of like an unsupervised metric. Okay, so now let's switch gears and focus on semantics, these things. So this is a concept map. And like I said, we want to have a concept map that describes the metadata. So when you're working with NHANES, you have this heterogeneous data set, all these different variables that have different meanings. And so we can use this concept map idea to organize them. So how you would read this is you would say, okay, urinary platinum, which is a possible risk factor, has the code URX UPT. So NHANES refers to urinary platinum as URX UPT within itself. If you look at the distribution of urinary platinum, you'll see that it's pretty right skewed. You'll also see that it's continuous. And so these, so the continuous and right skewed suggest ways of handling the analysis. Then you can also group urinary platinum within larger groups. So you can say that urinary platinum is classified as a heavy metal. And so if you are looking at urinary platinum, you might want to then go step up and look at heavy metals in general, because maybe they behave similarly. And then we're imposing the classification that urinary platinum is a study variable. So we're saying that we might want to find the association between platinum and whatever conditions we're looking at. Then we also know that in NHANES, heavy metals are measured within urine. So they're within the class of variables that are measured in urine, and that's important for reasons we'll get to in a bit. And so then similarly, we can talk about urinary creatinine, which is a different thing you can measure in someone's urine. And so this is a different classification. And for domain knowledge reasons, we say that urinary creatinine is a control variable, not a study variable. So that's why platinum goes to study variable, but creatinine goes to control variable. And then I'm also not showing all of this. So if this were like a true concept, make it easier to link to other ontologies, but that's not really necessary for now. And so then we can also do this for other different types of variables. So the variable breast cancer we see is binary. It's part of the class of medical conditions. It's not measured in the laboratory component, but it's asked about in the questionnaire. And so then to talk about Oshani's point earlier, we see that so breast cancer has the relationship with age at monarch has control there. So this is the ontology's way of representing that if you're looking at breast cancer, you should be controlling for the person's age at menarche. And then similarly, you should be controlling for their age. Now, if you're looking at diastolic blood pressure instead, this is a continuous variable, not binary, so that changes the modeling strategy. And we also, so diastolic blood pressure has a different set of associated control variables. So for diastolic blood pressure, you also want to control for age, but you want to control for sex, and you get this from literature. And so, and diastolic blood pressure has its own set of classifications.
So who makes these assumptions?
I do for the moment.
Using cadres or just?
Using domain literature. So you look at a bunch of epidemiology papers on PubMed, you see what they do, you mimic their study designs. It would be an interesting application of this to do some sort of direct NLP processing and try to extract study designs from papers without having to read them. But that's not what we've done so far. And then the other thing that I'm not necessarily mentioning is that there's not like a single set of true control variables. So different researchers think it's important to control for different things. And so if you wanted to make this more detailed, you would say, okay, like 50% of researchers say that you should control for age, but 99% of them say you try to control for age at monarch. And so you want to indicate some degree of confidence or certainty in these assertions. Are there any other questions about this sort of concept?
Yeah, sure. So you're going through some papers, finding these control variables.
Mm-hmm.
Are you tracking that provenance anywhere?
I
know breast cancer has a control variable age because papers 3 to 5.
So I have that information in my work, but it's not in the ontology as of now. So the risk browser doesn't directly present it. And that would be another good way of extending it and making it more useful. Okay.
Yeah, I'll put this in the agenda.
Okay. And then anything else? Any other points?
Well, why don't we, at the end, move back on that, because these are the kind of contributions that we've got to really nail down.
Okay. And so then finally, we have one more of these concept maps. And so this one focuses on the survey information. So like I said, you have this idea called a survey weight that's associated with every person. It has a code WT, and then it has a type survey variable. You also things like a survey stratum, and then a respondent ID. And so to emphasize what I said before, these concept maps are only based on the metadata. So you don't have a node in these graphs that corresponds to a single person or a single observation. You're instead working on the level of a variable or a class of variables. And this is done mostly for scalability reasons, and also just it seems like a good place to start. Okay, so now we can also use axioms to study to summarize our study design. So this is another way. So if you're saying, I look at a bunch of papers, I see what people do, then we try to represent this in a more formal way that you can then program into a computer. And so you have useful axioms like, if a target variable has continuous, then you should model using linear regression. If a study variable has measured in urine, then you should add urinary creatinine to your list of control variables. And so you'll notice these axioms are not all created equally. The first one is just a basic mathematical fact, basically. But the third one is something you have to deduce from domain expertise. And we don't have provenance that tracks that right now, but that's a useful idea to sort of incorporate. Then similarly, if a study variable has right skewed, you want to apply a log transformation to make the analysis better. And so then this last bullet point is the summary of the overall analysis scheme. So for every study variable, learn a model, report its results, and then aggregate them in some useful way.
Well, so this kind of loops into applying provenance. Could you imagine actually weighing, the source of that recommendation? Like, who says is maybe important?
Yeah.
Whether it's 99% say versus 42%, or perhaps just a source. Small number to say, but these sources are highly authoritative.
Yeah.
Could you envision that?
That seems interesting. Yeah. I guess another complexity is that not everyone says everything they've done in their papers. So if you look at the original EWAS paper, they don't actually say they control for urinary creatinine, but because the authors are some of the more distinguished epidemiologists in their field, you think they probably would, because papers by less well-known authors always mention the creatinine fact. And so you would have to sort of infer the degree of reliability, I guess. That sounds interesting.
But maybe based on impact factor of a journal.
Yeah.
Just to get it in a more concrete form.
Yeah, so you could do a vote of how many papers you would are weighted by impact factor or something like that.
Yeah, that's an interesting notion. It's the impact factor of that particular idea. So you've got kind of this inventory of factoids, and
you're presuming the rigorousness of the view.
Well, we're presuming that Hongxi's students kind of figure this corpus out and give it to
us. Did you have any other comments, John?
No, the modeling is helping to model this. And actually, facing the provenance will be a straightforward thing to add.
Okay, so just to summarize what we've just been talking about, we have a semantics analytics framework that's very modular, so we can add new conditions, we can add new control variables, which is good, so it's easily scalable. And when we group our different study variables by categories like heavy metals or phthalates, then that increases the interpretability of the results. Because even if you don't know what some specific phthalate is, maybe you know what phthalates are overall. And so that can help you as a researcher understand what a specific set of results mean. And if you had good namespaces and stuff, you could link this to other ontologies, which would be helpful. Okay, so now we're going to try to do a demo of the Risk browser. So we'll see how that goes. And so like I said, the Risk browser, it's an interactive web app developed in Shiny, which is a package for R that does applet type things. And so before we start, I want to thank the Darrell and NHANES team from last fall. So Claire, John, VJ, Kristen, Petey, and Andrew. So they did a lot of nice foundational work with setting up the browser, and they solved a lot of our early problems for us, which is cool. And so then what we want to look for is in the browser, so the effects of experimental design. So why are control variables useful? And then also semantic justifications for the experimental design. And then something more. Okay. So this is the browser's opening page. Does that look okay? So this is in the shiny. So we have our browser, and then so it just summarizes what it does, which is what I've been saying. Then there's a citation for the workflow, and we have a couple of different tabs. So the last one is the Cadre analysis tab, and that's not here yet. Mostly for reasons I'll talk about at the end and difficulty of information presentation. Then there's a couple of notes. So this is the population analysis view. So this is like the standard thing. So how you would read this is you're saying, okay, you're studying, you're looking for associations with thyroid condition. There are a couple of different options though. And so then you can see like how the model actually defines these different conditions. So in NHANES, you measure diabetes too by looking at someone's fasting blood glucose. But breast cancer, heart disease, and thyroid conditions are just answers on a questionnaire. And so then we also have on the bottom whether or not a target is discrete or continuous, or what model it needs. Then in theory, you could add more data sources to this, but we only have NHANES for now. Then you can say what control variables you want. So we have here the list of domain recommended control variables for each condition. So these aren't all the same. Breast cancer has things like age at menopause, or age at menarche and menopausal status that people don't think matter as much for diabetes 2 or heart disease. Thyroid condition has this thing called serum cotinine, which is a proxy for the amount of cigarette smoke you're exposed to, I think. And so then also at the bottom, we see that if we're looking at urinary variables, we want to control for creatinine. And so then you have a toggle option. So if you want to use the expert recommended variables, or if you just want to do your own thing, then like what categories of variable you're looking for. And then finally, the p-value threshold for significance. The standard is 0.05, but you can do other thresholds if you want to. Okay, and so now you look at the table of results. So first we start with risk factors. So this is a table with a lot of different entities in it. And so we explain what the columns mean. So you would think of this as sort of semantic explanation. For now, this is all hard-coded in Shiny, but if you were extending this and making it more semantified, you could make the explanations dynamic, like in the paper I mentioned at the beginning. And so for these control variables and this set of study factors, there are no risk factors. So none of the study variables seem to be positively associated with the presence of the disease, but we do have a bunch of mitigation factors. So various factors that are associated with not having the disease. And so you can see, so this is their full name. So URX UTL is urinary thallium, then where they came from, which is the last two columns. You can also have then the number of positive observations in the data set. So this is in this data set, the number of people who have a thyroid condition, and then the total size of the data set. So in cases where you have very small data sets, or even just a small number of positive cases, your results are less reliable. So you can take into account that. And then we can summarize our analysis at the end with two types of plots. So this is a Manhattan plot. So this is the distribution of p-values for the study grouped on a -log10 scale. So anything above this line is considered significant at our chosen threshold. And so we think that the association exists between these variables. And that's interesting. And then we can plot the regression coefficients. So these are 95% confidence intervals for them, so we can see how they vary. In this case, they don't vary all that much within each other. They're all kind of similar, and they're all negative. So now what you can see from this is you say, okay, this is all great and all, but you're not actually controlling for the right variables. So should we really trust these results? And so then it's easy then to rerun the analysis, and you can let it wait. What we're thinking of doing, so this is all in all of the analysis, and it's single core for now, but these problems are embarrassingly parallel. So if you were looking in larger problem sizes, you could pretty easily parallelize them, and that would make it just a little bit faster. And so now what we see here is these are kind of annoying. So what we see here is that once you control for the right variables, then all of the associations actually disappear. And so this is, you can think of this as sort of a reminder of why it's important to have this domain knowledge. So if you just jump into NHANES and start grabbing variables and looking for associations, you're probably going to miss important facts about your domain. And so then you want to have those represented in the modeling tool. And so then we also have the precision cohort analysis tab. So do you want to do a precision cohort or do you not want to do it? And so remember, with precision cohort, you're defining your own study population before you do things. And so there's a couple of different categories for this. You can say, okay, I want to look at children, younger adults, etc. You can focus on what ethnicities of people you want to study. So you can focus, looking for diabetes 2 prevalence in Hispanic people or something like that. Focus on gender and BMI as well. So now what we can try to do is we can try to pick another analysis and see if we can see if by getting a different study cohort, we can change the significance results. So right now I'm switching to heart disease and I'm using the recommended control variables, so the expert recommended control variables. And I'm still looking at phthalates and heavy metals. And so here we see that on a population level, there's only one risk factor and there's no mitigation factors, and so that's urinary cadmium. And so now if we try to reduce our population a little bit, so it's like look only at women, try all the ethnicities that NHANES has access to, focus on people who are roughly in the band of healthy BMI, and then you have to go back to this tab for the analysis to appear. We can wait for it to run. So then other comments on this. So right now this is a pretty fragile design. So if you do something like choose a precision cohort that has 0 people in it, which is possible, then it'll just crash. And so it's not very robust, and you'd want to fix that if you were doing other things with it. But here we see that, so if we're only looking at this specific subpopulation of female adults of healthy weight in these cohort years, then that association with the urinary cadmium goes away. So if you're changing your populations under study, you can change what resistances matter. Then the caveat here is that you have to be kind of careful how many times you do this. So like if you're really, really desperate to find an association between some pesticide and diabetes 2, you can probably find a study population with that association, but that doesn't mean it's reliable. And so you have to, because if you're just grabbing random slices of data, the distributions will be different. Are there any, so this is like what I was going to do for the demo. Are there any other questions on or comments on the design or anything like that?
That fourth tab that's not on there right now, what's that going to be?
So that's going to have cadre results. So from actual cadre modeling where the subpopulations are discovered by the model. The issue with that is that it takes a lot longer to run those models than it does these. So this is just pretty basic optimization problem, but with the Cadre stuff, you have non-convexity and non-smoothness. So what we're probably going to do as of now is just have a couple of interesting results already loaded, so you can see how Cadres work, but you can't necessarily generate new models yourself.
Is that something that can be parallelized?
It's implemented in TensorFlow, so probably you can do it on a GPU or something. I haven't looked into that, like how much speed you would gain, but it could be worth doing.
So the way you currently have the population analysis and the precision cohort analysis is super unintuitive.
Yeah, I agree.
But like, so either I would suggest moving that tab to be rooted within this tab, or to at the top, like print like which ones you're using,
yeah,
like, which subsets, and then go like suggest that if you want to change them.
Yeah, those are both good ideas. So my issue with like why I set it up like this was so the precision cohort analysis could in theory have this entire interface copied over in its tab, and that gets pretty messy. And so this is what I did at first, but you can definitely make it cleaner.
So the next tab is meant to be like an adjunct to the current tab.
Yeah.
Or maybe you could like, I don't know, I've never done this in training before, but maybe you could like have like something that you click to open so that you can open that. So that's not always showing, because if you want to just look at the same folder all the time, then you don't need to change it, but you like click it, open it maybe.
Yeah, or have it collapse, have it.
Yeah, exactly. Which I'm sure you can.
What's that called? Accordion?
Yeah.
How do you know if you just make your precision cohort too small? Because if there's no results, you can't look at any counts or size.
Yeah, so it'll throw an error right now. So what you would, like another way that you.
It ruins its significance too, right? Because if you just don't have enough.
Yeah.
It's gonna make it not fire just because there's not enough data. So you kind of have to know how much to count.
Yeah. So like what you could also do is on a precision cohort tab, before you do the analysis, it could show you all of your data set sizes, and then you could choose to continue based on that, or
Seems like you need that.
yeah.
Did it work for some of the precision tabs? Because mostly you just said it went away.
Yeah, I had an example written down that where if you, by switching to precision cohort, you lose some significance and gain other significance. But I think I left it in my office, so I don't remember what combination of study variables you needed.
You should have it default to that.
Yeah.
Real simple question, maybe you could answer. What, when you had all the risk factors, what is your default sort by?
So for right here.
Yeah, not in either. It seemed like it might have been alphabetical.
Yeah. So you can.
It seems like regression or.
Yes, you can make it sort by whatever you want, but it's probably alphabetical by default, which is not the most informative.
Source by the first column, and then you can choose the column.
Okay, yeah.
So for the use expert recommended control variables, it's pretty much choosing the control variables that when you hovered over it said use control variables.
Yeah, and it's not updating.
Yeah, so maybe it would make sense to update the list of control variables. If you click yes, then it adds the additional control variables.
Yeah.
But I think that's actually a shiny problem.
Yeah, that seems like it could be a shiny problem, just the little understanding of shiny that I have.
Yeah, so I picked up on the same thing, and I didn't ask the question because I'm like, I think this is a problem. but what we're talking about is when you select the, say, yes, actually filling in the form with those values.
Right.
So it's calculating it using those, but it's not showing that that's the case. So updating that form, and we need to have that, but we've got to figure out.
Yeah, because I don't know if you can have input variables in Shiny change other input values.
Well,
I don't think you can, but like one thing would just be the text at the top of
Yeah.
what
Yeah.
you're using, and that's just.
So Corey Byrne a year ago had exactly this problem doing the multi-window Shiny stuff. He couldn't figure out how to do it. So,
Probably can't. I would.
so yeah, Alex probably can't. I don't know.
Yeah. I would
Probably
be
can't.
surprised.
So Corey could.
Okay. Are there any other comments about?
So far, this is very cool.
It's just one more question.
Yeah.
So you're showing the Manhattan plots.
Yeah.
Are there options to show other plots?
No. So like the two useful summary plots we've hit on are the Manhattan plot and then the log odds ratio plot, or the regression coefficient plot, because those are both study level plots. What you would want maybe is to also have model level plots. So because if you're with like the heavy metals, you're running a bunch of heavy metals, but the only information you have about a given heavy metal model is a row in this table. And so you would want to have the ability to like maybe click on a particular model and then say, okay, how do the residuals look? So like more in-depth information. And that's part of the problems I'm running into with the Cadre stuff, where you kind of need that extra information. And so it's harder to put into this general framework. So let's go back to the presentation then. I just had a bunch of screenshots in case the demo broke. Okay, so like I was just saying, when you're switching to Cadre modeling, then a given model becomes a lot more important and a lot more complex. And so you don't necessarily want to reduce it down to a couple of numbers. And so you can get things like this. So for here, I chose a particular phthalate, this monocyclohexyl phthalate, and we're trying to predict the diastolic blood pressure. And so then the red error bar is what happens if you run a single population level model. Then the green and the blue are two Cadre model, is a two Cadre model. So a two Cadre model has two different linear models in it, and this is the first linear model's regression coefficient, and this is the second. And so what we can see here is that the second Cadre has identified a subpopulation that has a much stronger vulnerability to URX MCP than the population overall does. So this is the sort of thing you want to know about when you're doing Cadre analysis, but because it's model level information instead of study level information, it's harder to incorporate into the browser design. Similarly, you can say, okay, how do the Cadres differ by their predicted score? And so like what you would see here is that in the first Cadre, the first Cadre picked out people with sort of extreme blood pressures, so very high blood pressures and very low blood pressures, whereas the second Cadre, which is the one with a stronger vulnerability, picked out people with blood pressure sort of in the center. So here, how you read this is the x-axis is a person's true diastolic blood pressure, and then the y-axis is the model's predicted diastolic blood pressure. And so you can see how the errors relate and that sort of thing.
It looks like me or something, because like you have a noisy data.
Yeah, and so you have all these.
So you might need to put that in your modeling.
Yeah.
You said missing, also more.
Yeah, so this is like, these are people with diastolic blood pressures of 0.
Yeah, so
which
clearly they weren't measured.
I thought that, but NHANES doesn't say what to do when you have diastolic blood pressures of 0, but some people think that it's like a meaningful reading in some sense. I'm not exactly sure.
Sure, load your model. I guess you need a separate dialogue to get those people out of there.
Yeah.
Your model.
Yeah, I was hoping you would pick them up.
But it's interesting. Maybe it is an idea that another thing that semantics can help.
Yeah.
To remove nonsensical data.
And so then similarly, you can look at the actual Cadre populations. And so what this is saying is that the different Cadres have different distributions of ages. So the blue Cadre has more people who are older. So in particularly when you group by ethnicity, you notice these differences. So in this first ethnicity, the Cadre 0 has a lot of very young people, and Cadre 1 has a lot of older people, and then this general trend extends throughout. But so the overall gist, like these results aren't as important as what we've what I was talking about earlier. But like what I'm trying to get at is that when you're doing a more complicated model for precision health, you need to have a lot of specific information to help make sense of a model. And so like, do you want to have access to like 100 of these plots? Because if you run like a full EWAS with a Cadre, you get like several hundred plots that can look sort of like this. And you don't necessarily know to look for age and ethnicity, so it's kind of complicated. And at this point, we still require more domain people.
Well, but how do you present it to them? So you're probably, so what you're saying is that the blessing is the precision, but the curse is how do you decide?
Yeah, and so like as of now, how you decide is you just have a person look at the results of the model and look for things that are out of the ordinary with some sort of basic metrics to inform that.
But if you've got 100 of those.
Yeah, so what I usually do is some sort of filter system. So you filter first for significant biomarkers, and then within those significant biomarkers, you start looking at individual plots. And so you can sort of imagine doing that on the app, but it would be still a more complicated interface.
So you're imagining, here we go, a Cadre browser?
Yeah, some sort of Cadre browser. Okay. And so then I think this is my last slide. Yeah. So Deborah McGinnis said something pretty interesting a couple months ago. So she was asking me to reflect on this work, and she was saying, so what does your human brain think? And
gorilla brain.
as opposed to just like what happens if you just throw a random model at a problem and just blindly accept the outputs. And so what we've noticed is that, so constructing target definitions is difficult. It depends on what your data have. So you would rather have a more precise measurement of breast cancer, but in NHANES you have a very coarse, lossy, just yes, no question. And so that makes analysis difficult. In addition, labels can be heterogeneous, maybe more than is necessary. So if you try to model just cancer as your single response variable, well, cancer is really a host of different conditions. And so it's be capable of finding interesting associations. Although if you broke down those labels, maybe you could find better results. And then these are general, more facets of statistics. So this entire scheme of modeling that we've talked about really can't handle causality at all. A good example of this is that if you do use cancer as a single response variable, you'll often find a positive association with urinary platinum and cancer. And what this doesn't mean that if you have a lot of platinum in your urine, you're likely to have cancer. It means that, so platinum is often a byproduct of cancer drugs. So if you already have cancer and you start taking drugs to try to cure that, then that'll cause you to have high platinum in your blood, instead of the idea that having high platinum in your blood causes you to have cancer. And so there's a lot of complexity here that you have to deal with. So our approach so far can sort of handle the first one, where we have disease definitions and conditions in our knowledge graph or in our ontology. We can handle the complexities of that definition, but we still really can't handle most of these. And so these are useful things to look forward to and try to solve in an interesting way. So I think that's, yeah.
Can you explain the fourth one? I'm curious, because I don't understand.
Okay, so this is the phenomena of a confounding variable.
Oh.
So yeah, so like if you add, so a variable will explain some amount of variance in a model. Yeah.
Okay.
All right. So let's thank Alec. If there's